Okay, semiconductors. Band theory. So this has nothing to do with music. Band theory is a model for metallic and covalent solids that came out of molecular orbital theory. So atomic orbitals in the crystal combine, they're delocalized over the entire crystal. So you've got molecular orbitals. So in some sense, we can think of a crystal as being a very large molecule. It's a really big molecule. When atoms form molecular orbitals, you have the bonding orbitals and the anti-bonding orbitals, right? The bonding orbitals are lower in energy. The anti-bonding orbitals are higher in energy. When you have all of these same atoms together, the bonding orbitals are going to be occupied and the anti-bonding orbitals are going to be empty. And as you get more and more atoms in this crystal or this molecule, then the difference in energy between the bonding and the anti-bonding orbitals becomes smaller and smaller. So let's look at this. So here we've got one lithium atom, and there's the one valence electron in its s orbital. And if we put two lithium atoms together, they each bring one orbital, and so we end up with two orbitals now, a bonding and an anti-bonding. 4 lithium atoms, we're going to have 4 orbitals. We're going to get bonding orbitals and anti-bonding orbitals. As you continue to add lithium atoms, the energy difference between these levels becomes smaller and smaller and smaller. So once you get a piece that's large enough to actually see, you've got occupied orbitals, which are called the valence band. These orbitals are delocalized, spread throughout the entire thing, the entire molecule. And then you have empty orbitals, the anti-bonding orbitals, and those are just slightly higher in energy, and they're just sitting there empty. Any questions? This is kind of rough on Monday morning. So electrons can become mobile when they move from the molecular orbitals in the valence band into the higher energy, empty molecular orbitals, the conduction band. In metals, there's no gap in energy between valence and conduction bands. The electrons can easily just jump up there and move along. So metals are good electrical conductors because the electrons in that conduction band are mobile. And that also explains heat conduction, because as the mobile electrons move, they take their kinetic energy and spread it out throughout the piece of metal. Okay, so that probably didn't make a lot of sense. Here we have a conductor. The valence band is going to be full of electrons. The conduction band is going to be empty, but there's really no gap here. So my analogy for this is the highway, the freeway, and there's a traffic jam. It's stopped. It's just completely stopped. These cars cannot move. The cars are the electrons. They can't move. This is like the shoulder of the road, right? There's nobody over there. Now, you know you're not supposed to jump out of traffic and drive on the shoulder, right? No energy gap means there's no penalty for doing that. So, of course, some people are going to do that, right? So a car can move out of this stopped traffic onto the shoulder where there's open road and can just move along. And so that's how metals conduct electricity. There's no penalty. There's no energy gap between them. In an insulator, there's a valence band and a conduction band, but there's this big energy gap. And so these electrons cannot move up there to become mobile. So this would be like, when they have those concrete barriers, or maybe there's a cop sitting there, and you know that you're going to get this big fine if you jump off into the shoulder, so you're not going to do it, right? There's a gap here, so nobody moves over there. Insulators do not conduct electricity. In a semiconductor, we have this intermediate situation. There is a gap, but it's only a small energy gap. And so some electrons will go up to that conduction band. And with a semiconductor, you can change the conductivity of the substance fairly easily. So this would be like a small penalty for going onto the shoulder. It's like, well, yeah, I'm going to be caught, but it's going to be a $10 fine, right? And I'm late for work, and I've got an important meeting, and it's worth it. So some people are going to take that penalty and go. Does that make sense? For semiconductors, the conductivity increases with temperature. So as this is heated up, the electrons in the valence band have more kinetic energy, and so they're more likely to jump into the conduction band, and so the semiconductor becomes more conductive at higher temperatures, less conductive at lower temperatures. With a conductor, it's always conductive. With a non-conductor, an insulator, it's always an insulator. There's not a temperature dependence for those guys. If we look at the magnitude of that band gap as we move down the group 4A elements. For carbon, in the diamond form, not the graphite or buckyballs or graphene or anything like that, but just carbon in the diamond form, the band gap is 5.5 electron volts. That's a unit of energy. And so that's classified as an insulator. Diamonds don't conduct electricity. There's too big of a gap between the valence band and the conduction band. Silicon has a smaller band gap, 1.11 electron volts. It's considered a semiconductor because it's kind of in between. Germanium is also a semiconductor. Its band gap is 0.67. And then tin and lead, tin has a very small gap, 0.08. That's not really much of a gap, and so that's a metal. And then lead has no band gap, and so that's a metal. And so we see as we go down a group in the periodic table, we're getting from a non-metal to a more metallic character, and in between are the semi-metals. Any questions? This happens because as you go down, those atoms are getting larger. And so the overlap between the orbitals becomes less because they're getting bulkier, and so that's going to reduce the energy difference between the bonding and anti-bonding orbitals. We can control the conductivity of semiconductors by what's called doping. This has nothing to do with drugs. Doped semiconductors have small amounts of impurities. So the impurities can cause there to be extra electrons. The valence band is full. Those extra electrons have to be in the conduction band, and they're always in the conduction band, so that increases conductivity. Or we can be electron deficient, and that causes electron holes in the valence band. So an N-type conductor has extra electrons. So if we take silicon, which is a semiconductor, has 4 valence electrons, and we put a little bit of phosphorus in it, phosphorus has 5 valence electrons. So that one extra electron from the phosphorus atom doesn't fit in the valence band because it's full. So it has to go into the conduction band. So you have some electrons in the conduction band all the time, and so the conductivity is larger. In this situation, what's carrying the charge is the electrons. Electrons are negative, and so this is called an N-type semiconductor, where the electrons there's extra electrons, they're in the conduction band. The other type is a p-type, and this has electron holes in the valence band. So how does that work? Well, again, let's look at silicon. 4 valence electrons, and now we'll replace some of the silicon atoms with gallium. Gallium has 3 valence electrons. So now in that valence band that was full before, because some of those atoms only have 3 valence electrons, there's going to be some holes in the valence band because we're missing some electrons. Those holes can move. How does a hole move? Well, think of the stop-and-go traffic on the freeway. What if that gridlock situation, what if you went in and took out every 10th car, just like vaporized it, right? It's gone. Could traffic start to move? Sure, because this car behind the hole that was created can move into the hole. And now the one behind can move into the hole created by the first one moving. So we think of the cars moving forward, but you can also think of the hole moving backwards. That make sense? Kind of, sort of. So because here we don't have electrons moving in the conduction band, we have holes moving in the valence band. It's called a p-type semiconductor because the hole acts as a positive charge. So silicon chips are essential in computers and any other electronic device. And these contain millions of p-n junctions, where you've got a junction between a p-type semiconductor and an n-type semiconductor. And these can act as diodes, which allow current to flow in only one direction. They can act as amplifiers, which take a small current and make it into a larger one. So these semiconductors have just completely revolutionized computers. When computers were first created, instead of semiconductors and little tiny silicon chips, they used vacuum tubes. And so a computer that could do less than the calculator you have in your backpack occupied an entire basement of a large building and could only do very basic things. But now we've got really incredibly powerful computers in our cell phones. I mean, it's really kind of mind-boggling what we've been able to do. Okay, so here's a question. Which element would you dope into germanium to create a p-type semiconductor? Well, in a p-type semiconductor, do we have extra electrons or are we missing some electrons? We're missing some electrons because removing a few of the electrons gives us the holes that can move, the positive holes that can move. So germanium, how many valence electrons does germanium have? 4. It's in group 4A. It's got 4 valence electrons. So then for a p-type, we want something with fewer valence electrons, right? So we've got indium. Indium's in group 3A. Would that work? Yeah, it's got 3 valence electrons. Let's check the others. Tin. Tin is in group 4A. So that's the same number of valence electrons. And arsenic is in group 5A. So indium's the only one that's going to work. What would we get if we put arsenic in the germanium? We get an n-type. Because the extra electrons from the arsenic can't fit in the valence band. They have to go into the conduction band, and so that would increase the conductivity. Any questions? So this is touching on electronics, right?